Okay, can I have your attention? I think we'll start. I would like every child under the age of 25 to have a piece of chalk. And if you don't, try to get one. There's some which I'll stick on the end of the bench here. We need them so you can all participate in an experiment. So, I'm Jim Fuller. I'm the wizard of the day. And I'm a physicist. And this puts me at a disadvantage from the previous speakers who are mostly chemists. Because chemists have the advantage they can have things that go bang. And when things go bang, the little kids and even the big kids like it. But if I were to do the physicist kind of bang in here, no, you wouldn't like it at all. So we won't have any bangs. So instead of talking about bangs and smoke and things, we're going to talk about the most essential ingredient that a physicist has, and that's his mind. And we're going to talk about physics, and we're going to talk about how physics applies to sports, and how, as a physicist, you can think about sports, and as an athlete, you can think about sports in a way that's exceedingly useful to you. So, I'd like to show a view graph here. Just what I'm going to try to do during this whole presentation is to make something that's fairly complicated as simple as we can conceivably make it, because there's absolutely no reason that science or thinking has to be complicated. Now, I will confess one of the problems that I have at this university is this Wizard of Id cartoon, which points out the knight says, "Why are athletes worshipped and do scientists go unnoticed?" I'm a scientist. "Would you buy a ticket to see a scientist?" "No." And the king says, "There you are." So I thank all of you for coming and bringing your kids this morning during spring break starting. I will talk a lot about how you might design a better way of doing something in athletics to show you the sort of counterexample of what you don't want to do. Most of you know what crew is. We have these little boats and you have a bunch of guys rowing. Let me show you what the crew team would look like if it were designed by the university's central administration. Somehow or other, you'd put more rowers in there if you were thinking about it, I would have guessed. Okay, so the music that you've listened to is mostly sports music. It's all over there, what I've done. And the very last piece was the theme from the Chariots of Fire. Some of you, I'm sure the adults have seen it, maybe the children haven't. It's a great movie. It's a story about two British, one Scottish and one English runners, Harold Abrams and Eric Liddell, both of whom managed to win gold medals at the 1924 Olympics in France. In this story, basically, it shows how Harold Abrams used a coach to help him do better. And if I can have a little bit of the first of the view videos now. This is just a little bit taken out of context, slightly separated out of this wonderful movie, Chariots of Fire.
Mr. Mussolini, I can run fast.
We need some light.
With your help, I think I can run even faster. Perhaps faster than any man ever ran. I want Olympic medal.
This is Harold Abrams, this is Mussolini.
It's waiting for me. But I can't get it on my own.
Well, if it all stays like there's some, you can put in what comes after. And you leave it to me. I'll watch you, I'll observe, and if I think I can handle it. Well, I can see the big prize I had. Believe me, I won't waste any time. When we meet again, I'll bet on it at the beginning.
So you will watch me?
So, if you're good enough. I'll take you apart piece by little piece.
Thank you.
This is a trial run in London just before the Olympics where he's running against Eric Liddell and loses, as you will see.
Get set.
This is Harold Abrams, and he lost to the Scottish runner Liddell. This is sitting sometime after the match is over. A depressed Abrams, he's not going to win the prize. The Olympic medal, he feels. Now his girlfriend consoles him.
It's not the losing sin. Liddell is a fine man and a fine runner. It's me. After all that work, now God knows what I aim for. Beating him the next time. Still, I can't run any faster.
Listen closely.
I can find you another 10 yards.
Okay, stop. What he said was, I can find you another 2 yards as a coach. That's what science, physics does for sports. It finds you another 2 yards, another 200ths of a second, another just a little bit higher on some motion, because it's measured. Olympic medals are given out in seconds, milliseconds, thousandths of seconds. Just a little bit more, and certainly less than 2 yards makes an enormous difference. So I wanted to talk about how you could think about these things. But first I wanted to put down what physics is and try to keep track of what it is. Physics is a useful way of thinking. That's all it is in many ways. It's just a way of, how do you think about these things in a useful way? So I would like to show the one example where technique made the greatest improvement in sports that I know of, and that's in the high jump. If I can have the video again, the next one, it will show the Fosbury flop. It's very short, but notice the person won 6 centimeters in the height he was able to jump by changing technique. So can we have the video? That's Harold Abrams, by the way, actual picture.
But thanks to one man, the high jump and the pole vault have changed dramatically. The old approach of throwing yourself over the bar remained the only way to jump right up until Mexico in 1968, when Dick Fosbury had a different idea. Fosbury's flop shocked everyone. Curling himself around the bar, Fosbury won gold and produced a world record jump 6 centimeters up on the previous Olympic record. Biomechanic analysis has revealed why this startling change in technique worked to such great effect. Under the old styles of high jumping and vaulting, the athletes set themselves the tough task of getting all their weight over the bar at the same time. The secret of a Fosbury walk is in the curve of the athlete's body in flight. Their weight is transferred over the bar in stages. At this point, for instance, the head is over the bar, and the body and legs are below it. While now, as the legs are curving over the bar, the head is already on the way down. It was an inspired innovation in technique, allowing the athletes to use energy more efficiently and consequently jump higher.
Okay, stop. Now I'd like to have a volunteer. Okay? What I would like you to do is I have these 3 wastebaskets here, and I'd just like to see, I'd ask you to stack them for me so they're all together in one giant stacked wastebasket. Very well done, in fact. She did it the way I didn't hope she would do it. Will you do again what you did? Because it applies to what Mr. Fosbury did, okay? Go, do the same thing. Thank you. Gorgeously done. The alternative, which was done before Fosbury, was this. Does everyone see the difference? In one case, she did it the most efficient way. What she did is she lifted one wastebasket, and then she lifted one other wastebasket, producing the stacked set. If one had not done it that way, an alternative would have been to lift one wastebasket and then lift 2 wastebaskets. That meant I've lifted 3 in order to cause this to happen. Okay? Now, how does this apply to what Mr. Fosbury, what you've just seen? Suppose this is a human being. Okay? This is a very close approximation, actually. Basically, the old style of high jumping was like this, where you got all the wastebaskets, so to speak, over the bar at the same time. Where did the energy come from to get all this stuff up here? It came from the push-off, right? What Fosbury noticed was you can go dum, da-dum, 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 and you can come up like this and get this part over first, and then, while this is now over and long gone, this comes up and comes back down. In that process, if you look at it very carefully, he never really, at one time, gets over the bar. This means that the amount of push it required his legs to do only needed to get him up to something about here. This is obviously easier to go this high than it is to go this high, right? Just by changing the technique. What he noticed was the high jump doesn't take place instantaneously. Boom. It takes place in time. And so you can do certain things at the beginning of the high jump, certain things at the end of the high jump, and this produces an enormously better jumping situation where the same amount of push will get your whole body sequentially over a higher bar. Okay? The same is even more obvious in the pole vault. Pole vault, the guy comes along. This is the pole. That's just about right. So he's got the pole, and then he bends it like mad, right? Puts all his energy in the pole. Then he swings up. His feet are up. His head is down. He's up here. He curls over like a snake. And he never really jumps over the bar. So basically, that little change in technique was the thing which caused 6 centimeters, that much, change overnight from one Olympic time to another. That's an enormous increase simply by looking at what physics is doing. So what is physics? Physics is also, we could make it colorful, efficiency. of motion. The rule says I just have to get across the bar. The rule does not say I have to get across the bar all at the same time. This makes an enormous difference. Now, if we can have the video, I'd like you to look at something which I think is done wrong, I haven't asked anybody, on the broad jump. Let's look at the broad jump.
Today, computers draw the lines and offer an almost unparalleled opportunity to study technique. At Barcelona, scientists compared the long jump techniques of Carl Lewis and Mike Powell, and they spotted a difference in styles that may have given Lewis the edge. The most effective way to long jump is to take off fast and jump straight. Lewis, with the dark hair, maintains a very straight line. Whereas, looking from behind, Mike Powell on the left of the picture can be seen twisting his body as he pedals through the air. This twisting of the body combined with Powell's minutely slower takeoff speed may be why this time it was Powell's turn to wear the silver.
Okay, thank you. Could we show it if you looked at it, but we won't have time to do that, is that when they landed, their hands were in this position. They were somewhere off to the side, okay? Just like it's better to come over like this, it would be better if just before they landed, what counts is where your feet hit the sand or where your bottom hits the sand. If they would have done this, the very last motion that a broad jumper should make, I believe, is to do this. Because what is that doing? That's basically letting this mass of the arm go back. That tends to move the center of the whole body forward. And it makes a difference, by my calculation, about of an inch, which would be a significant amount even on the broad jump. So that's a possibility that the world hasn't necessarily done things perfect yet in terms of analyzing the physics of everything that they thought about. I have meant to call up the Olympic Center and say, I need to talk to the broad jump coach. I'm going to do it because I think it's right. And after all, it took a long time to find Fosbury could have been done 30 years ago, and it wasn't, simply because no one recognized it, okay? So now we will do, I thought I would tell you what I do in the morning when I get up. What do physicists do when they get up in the morning? Well, I always have by my bed a box of chalk. And I always, on the rising, get out, take a piece of chalk, break it in 2 unequal pieces, and stand there and wonder that they fell at the same rate, okay? Now, I've sat in the back and watched other of these Mr. Wizard things, and the kids up here always get selected, and the little kid next back there, oh, Mommy, I didn't get selected. So now you're all selected. You all have a piece of chalk. So all those under 16 can stand with their piece of chalk, break it into 2 unequal pieces, Anybody need a piece of chalk? I hope. That's still close enough, okay? As soon as we get the chalk distributed, let me show you while everyone's getting their chalk ready what I did not do. What I did not do is break it into 2 unequal pieces of chalk, get out my stopwatch, and which naturally I don't have by the bed. And so we put here and measure the time. You have to get your new piece of chalk. Write it down, right? Some crazy number. Let's say 0.31 seconds. Then I take the big piece of chalk, measure the time, write it down, and subtract. Okay. This is what I don't do, okay? Why? Because that's poor science, poor experimental technique. basically, I could screw up in the subtraction, right? It could be that the wind blew differently. It's much better to do a differential experiment. So now, if everyone has their pieces of chalk ready, and I want you to just pay attention to your chalk. We're going to let them go, and you notice if they hit at the same time. Ready? Go. Okay. Anybody's pieces of chalk not fall at the same rate? Okay. So let's write down some other features of physics. The rules apply in this part of the room, they apply in that part of the room, they apply in Denver, and as we'll see a little later, they even apply on the moon. Okay? That's gorgeous, because if Mother Nature changed the rules every time, there'd be no hope. She's subtle, but she does not deal off the bottom of the deck. Okay? So, now we've just shown that two different sized pieces of chalk fall at the same rate. Suppose I went to enormous expense in your honors. I have here a bunch of things. Here's an orange and a green apple. And they fall at the same rate. The next one will be apparent to you. This is an apple and a pear. They fall at the same rate. However, if I take a feather and try it against, say, the orange, they don't fall at the same rate. So it must be that in spite of the fact that the rules of physics and chalk when I get up in the morning seem to work, that there is a subtlety there. There's that 2 yards that Moshe Bini was talking about that was a little, could be obtained. What could I do to make the feather fall faster? Any ideas? Yeah. Give a little weight to the feather. Excellent idea. Any other suggestions if I don't want to do that? Yeah, back there. Crumple it up. Yes. Yeah, you? Pardon? Cut off the feathers. Then it's not exactly a feather, is it? But it would be close. Then you, pardon? Wet it. That works good. And one more chance. Perfect. Right. We could put it in a vacuum, right? So let's do that. Here is a tube which consists of a penny, and it tells you something about the budget for this program, doesn't it? And a feather, which is not really a feather, but it's a piece of tissue paper. And anyway, if I do this, you can see that the penny got in the way, but the feather, or the piece of tissue, falls a lot slower. So now we're going to just pump it out with this vacuum pump. And for anyone who happens to know, I know this is an illegitimate demonstration, because what I'm going to show you is shown wrong in every textbook in the country. Because, in fact, what I'm removing is the v squared dependence, not the v term. Because this pump doesn't get me there. What this gets rid of is the swirliness of smoke things when you go down, not the smooth linear flow. But, nevertheless, it's what's usually called getting rid of the air. So we'll close it down, hopefully. And it looks like we might have a semi-vacuum. Do that. Put these here. Whoops, the penny stuck. We got this from the low bid. Clearly it falls at a much improved rate, okay? So now we have the last, a very short video. This video was made long before you were grown up. This was made in the 70s. This actually shows on the moon the astronauts, the reason it came about was because on Apollo 14, someone had a golf club and hit a golf ball, and that was bad public relations. We're spending billions to hit golf balls on the moon, right? So Joe Allen, who was the scientist astronaut from Yale, actually, is a Yale undergraduate, said, hey, we'll do something useful. We'll drop a hammer and a feather in the vacuum of the moon and see that it works. So can I have the video?
Apollo 15 astronaut David Scott explored the airless surface of the moon. He couldn't resist repeating this classic experiment for all the world to see.
Thanks. Actually, that experiment has more than you know about it. The feather, since it was an Air Force guy, was actually to be a falcon feather. I don't know how they got it. Falcons are not very friendly, okay? Furthermore, NASA was very much concerned. You know that if I take a comb and I just have a piece of tissue paper, at least it used to work, I don't know, there's less hair than there used to be too. You know, so to get it charged up like this, usually electrostatics causes problems, basically. NASA was worried that they would have this feather sticking to the astronaut's glove in the vacuum of space, right? So they thought about weaving little wires in here, gold wires to make conductive and so on, adding weight like some student said. But in fact, they decided to be honest. This was the previous NASA. But at any rate, they thought they'd rehearse it. And so Joe Allen, the plan was when they were off camera to drop the feather and do the other thing and see what would happen. And so they'd know it would work. So after the thing had successfully, as you saw, being done with Walter Cronkite making the call, said, hey, that's great. Did it work the first time you tried it? And the astronaut said, Joe, you saw the first time it was tried. They just didn't have time to try it out ahead of time. So basically, that thing was supposed to have been tried. One of the things that you try to do to make things fall better is make them aerodynamically shaped. Could I have off that thing up there? This is a bicycle, a little more expensive than the ones that you may have come here on, because each of these spokes is in fact shaped like an airfoil on an airplane, so that it minimizes the air resistance or the drag of this, so this particular feather going along, this is Miguel Indurain in 1992 Tour de France time trials. So this is one trick you see with expensive bicycles. You can buy these, but your parents won't like you to know about them. And here's another one's front similarly. Why not? And the back is just a solid disc. You don't put a solid disc in the front because when the wind blows crosswise, which you have to deal with, makes this very unstable because it gusts at the wrong moment here. So the best wheel is the solid one. And this is just to make this particular feather fall faster. Okay, now I want to talk about basketball because basketball is sort of in right now. And so I would like to tell you what the first rule, the first theorem of basketball is. And the basketball first theorem is, that one leaked. This one's okay. The first theorem of basketball is if you expect to score, the diameter of the ball had better be smaller than the diameter of the hoop. Otherwise, you know, it gets there and the announcer says, I think there's a problem. Okay, so that sounds very trivial and simple. Now I need 6 volunteers. Okay, you in the blue, you in the red, you with the glasses, you. and you. Now, if I could count to 6 correctly, okay? I want you to quickly line up in size of height. So we'll put the little one on this side, and we'll get taller going that way, okay? Hey, pretty good. Very well done. Great. Well, I don't know about that, son. I think you're being very proud, but that's okay. That's great. Okay. So now I want you to come around in this order. Come on. And we're going to take you one at a time. And I want you to get up on the... So can you climb up the ladder? Or I can pick you up probably. Okay. Don't fall off yet. So, now come here. Now what I want you to do is your job is to just drop the ball through the basket. Perfect. Okay? And you will be the ball retriever, right? However, don't do it yet. We make life a little more difficult since you're bigger, right? We move it to, say, here, 15 guys. Okay, let's see, you drop it through. Perfect. You score 2. Okay, so now we'll go crank it over a little bit more. Okay, you got it? And yours is going to go just a little bit more. That's what's known as a dunk. Can you get down? Okay, now we're running out of talent here, so we're going to make it a little harder here, right? All right. But did you notice what happened? He rimmed. He hit the rim, but he scored, so that's okay. Okay. And we have one last contestant. Wait. No, no. Okay, that's fine. I think that all of you can see that there's no way beyond some point that this thing is going to go through at this place, okay? This is why the coach says, if I can find the right view graph, put a little bit more arch on your shot. The important, this is a beautiful picture, but it didn't come out very well when it was done by the company. This angle of the ball approaching right between here and here has to be greater than 30 degrees in order for the ball to be able to go through missing this side and missing this side. As soon as it becomes less than 30 degrees, in other words, a flat shot, you have almost no chance of having the ball go through, okay? So let's look at a little bit more in the efficiency of motion things. Well, let's look at basketball for 1 second, basically. Here's an early game of basketball. Looks pretty fun, doesn't it? Notice anything unusual? What do you notice? That's right, it is a basket. It has a bottom. Anything else do you notice? And no backboard, okay? No basket, there's no hole in the bottom, and so on. This picture comes from 1892. If we look in 1896, 4 years later, okay? First, the good news is, or the interesting news is, that in fact this was also played by young women already back then. Here we see, there's the basket, and it has still the same incredible characteristic. It has no hole in the bottom, right? The scores of the games were fantastic, like 7-5. Because after you scored, you know, there was this long delay while you shinnied up the pole and got the basket out. And incidentally, the reason the backboard was introduced was to keep young enthusiast hands from interfering with the ball who were sitting just behind the basket as it was shot. It wasn't as a vehicle to bounce the ball more efficiently in, but it was to keep the audience participation down to a reasonable level, okay? Why do you think it took so long for this to happen? The answer is, I think, the following. Ideas are really hard to come by. We spend so much of our lives doing the same dull and boring and uninteresting thing, looking over there where nothing's happening, and it takes a genius to point out that if you cut the hole out of the bottom of the basket, you'd see something quite different in terms of the character of the game. Okay, so now I need another volunteer. This time I need outstanding basketball players. We only want to see those who are outstanding. Okay, he's modest. He said he's not outstanding, but he's good. We'll use him. Okay, come on. So, we're just going to improve on your game. You're there. I dribble, right? I pass you the ball, and then I want you to jump up and shoot like there was a basket here, but try not to wipe out the expensive camera, right? So, sort of like to me, right? I'll catch it here, okay? I'm the thing, okay? Okay. Let's do it once more. I want everyone to watch very carefully exactly what he's doing. Okay? Now, I am going to not win him 2 yards, but I'm going to win him 0.2 of a second in his basketball game for the rest of his life. What does he do? He does the same thing the CU men's team does. He catches the ball, he bends his legs, and then he goes up. Okay? What he's doing, I don't know. Maybe he didn't drop the chalk in the morning, right? He's doing the experiment. How long does it take me to fall this far after he's got the ball? Why not, this time, have your legs bent? Right. When you see the ball coming, you get prepared for the shot. Okay? Are your legs ready? Up. Okay. In this process, he wins the amount of time it took him to drop this far. Basketball players and chalk fall at the same rate, actually. Chalk is cheaper. Thank you. And so by just changing this one little detail, he'll be the sort of player in the future where the announcer says, when he took the three-point shot, he's got a tremendously quick release. Why is he any quicker? Does time run slower? No. He just catches, watch. The people who have quick releases, if you watch your replay, they'll catch the ball ready to spring up, okay? Now, one of the things about physics which is good is that it's not only universal, but it applies to many things. Who's a good cross-country skier? You. Let's see, are you going to fit inside of my shoes? You got very big feet, madam. Okay, kick your shoes off. Can you do that quickly? Great. And can you ascend from the back way here with both shoes off? Thanks. Okay? I think they'll just sort of, I think you'll be able to slip your foot in there, be all right. These are probably a little long for you. Okay? Perfect. Lace them up. Even a little big for her. I'll get you your poles in a minute. Don't fall off, right? This is not an exercise in recovery. These are probably a little long too. So first, how do you hold the poles when you pull? Or what motion do your poles just pull along without it? Okay. Notice the sin which a lot of people, I'll sin. It's easy for me to sin. I'm not very good at this. A lot of people are planting, whoops, sorry. It's dead. A lot of them plant the pole, but this doesn't do anything. The only thing useful is the motion, I want to go this way, which means I want to push back this way. She did that rather well. Okay, now if you stride forward without falling off, show me what you do. Just take one stride and stop. Okay. What she should be doing, and it's difficult, but let me just stride forward. Go ahead. You should be down, this should be down, and it should be in that position, ready to hop up as soon as the foot is in the forward position. Okay? Right. And what is this similar to? The jump shot. Okay? It's exactly the same thing. If she ends up with her foot here, don't bend it yet, and then gets there and says, ha, now it's time to push off. Now I'll bend my knee, right? And then I'll go forward. Then she'll wonder why all the Norwegian skiers are so much faster, right? First, they're probably better, but maybe not. But it's a question of technique. And the same technique that applies, the same idea of economy of motion applies to basketball and cross-country skiing. Thanks. I'll get these off here. I think I'm going to show you a video that shows the Olympic Center. So if I the next video, it talks about swimming. Swimming is something all of us can do. This takes 2 minutes, but it's okay. Notice how he came over.
Nature advances like raspberries are rare. But here at the U.S. Olympic Training Center in Colorado Springs, scientists are looking for ways to make biomechanics an integral part of an athlete's training. Head of Biomechanics, Sarah Smith.
In the process of getting to a competition, we would like to have biomechanics have a part in providing information to the coach that can then go immediately to the athlete so that these minute flaws in technique can be eliminated as early as possible and the performance be ingrained in the motor pathways of the athlete so when the time comes that we have the very, very best performance possible. This is a side view of the balloon pattern.
In early 1992, scientists in Colorado Springs turned their attention to Dara Torres, U.S. Olympic swimmer who was in danger of losing her place in the women's relay team. Her technique appeared inefficient, but exactly where and how Dara was wasting energy, the coaches could not be sure. It was time to put Dara through her paces in the Aquatic Research Center's multi-million-dollar swimming treadmill known as the Flume. The test, devised by scientist John True, meant Dara had to swim for half a minute at world record pace.
Okay, Dara, we're going 30 seconds. Let's go.
To make things just that little bit more difficult, True made Dara wear a mask to measure her oxygen use during the test.
Okay, Dara, let's go. 15 seconds. We're going to go. Let's line in.
Look at her hand.
Against a powerful current. Just to stay in place, Dara must swim at world record speed. All the while, high-speed cameras are recording her stroke, and from this information, the computer analysis is prepared. Notice how Dara swims with her fingers very slightly apart. This is now common practice among top-level swimmers. One of the early successes of computer analysis revealed that water trapped between the open fingers produced a greater hand surface area, almost like having webbed fingers.
Great. Okay, so I had seen this, and so I thought, is this true? Is computer analysis correct? So I thought I needed to show you how you could actually measure something, and so I've tried to build an apparatus, okay? What we've done is I've made it two large pools. Now, one of them has a small leak, so we'll fill it slightly. Either that or it evaporates very fast. I suspect it's the leak hypothesis is right. So basically I made something that looks like a human hand. Can the television show this up there? You can see these 4 fingers, and they're actually scrunched together, okay? The other one is exactly the same. 4 fingers scrunched together. This was done on a computer-controlled milling machine in Gila, where I work. And so basically they are as identical as we could make them. Now we need to have the view from here. What I'm going to do is to make this automatic release mechanism. That's I go. I'm going to pull this. You're going to see these 2 hands do this. That's the swimming motion. They have the fingers tight together, okay? Why are we doing this way? This tells me nothing. I mean, you'd expect them to be the same. But this is the beauty of differential measurements. You better make sure that 0 is the answer before you begin to discover whether opening your hand does anything exciting or not. So, well, you'll watch as these come down on 3. 1, 2, 3. So were those essentially the same for those who had no parallax? Okay? So the next part of the experiment, after the flood, I hope you all brought your arcs, is we will change the fingers on one of them. And I have a handy helping sheet here. This is what's so fun about science. Science, things happen. So now I'm going to open this up. And move these fingers out, simulating what they tell me by computer analysis should produce greater drag, and therefore it should fall slower. We move these out a little bit, and I'll show you what it looks like in a second. We have to tighten this. The reason I did it this way rather than pivot them out is I was worried in pivoting I'd change the cross-section of the area that we were looking at. So this was done with some sense of let's not cheat the kiddies in this process, okay? So now let me just show you what it looks like. Can you show with that camera? Notice there's a spacing between here now. So now we have a simulated hand like this, which will be swimming against a hand that looks like this. So we have to rescue the other one from the grate down there. Find the piece of metal, thank you. Bring it up. Refill the tanks because I want to have water in them, as similarly it was. Okay. Might have enough here. The reason I want the water in here, by the way, is what I don't want to have happen is to have the hand slap the water. Because if it's not dead level, because this is terribly unlevel, then it tends to hit it and go one way or the other. And if it hits the side, the game is off. Okay, now we need to have some very good judges in this area. So could a couple of you sit dead square? You have to sit along this line. So a bunch, yeah, please. Line up and you'll be the judges. Yeah, you too, right here. And you can sit on a higher step. You can look over them, right? And you're going to watch these 2 hands come down and see whether the one in front or the one in the back or both of them get there at the same time. You are going to see a parallax problem. That means you're looking at a skewy angle. Come here. Okay, you look over her shoulder like you're umpiring, right? And you're umpiring too, right? Okay? Okay, so here we go. This is the one which, according to the Olympic computer analysis, should have less drag there, so it should go faster, and this should go slower. Ready? 1, 2, 3. This one won, right? Just the opposite of what the multi-million-dollar tank and computer analysis suggested. So then the question, and when I discovered this, I thought, my goodness, why is this the way it is, right? So now we have to look at that question. Find the right view graphs. Must be in this pile. Okay, 3 pictures. This time I have an adult cartoon. Some of the cartoons are actually too complicated. Here's the first one. Very often theory is gorgeous and experiment is somewhat more difficult, okay? From the point of view of, this one will be difficult for you, the kids, but for the adults, it's sometimes exceedingly hard to point out the culprit. And one of the most beautiful expressions I've ever seen was this thing by J.R. Pierce, who I'd love to know who he is. Much more is known than is actually true. So I don't really know whether my model is not good enough. I actually made them go at different rates. I don't think that's the issue. Maybe my hands were too far apart, but if I watched very closely the woman swimming in the Olympic thing there, and her fingers were this far apart. Now, it may be that 2 things. When I spread, I'm not a duck, but a web does appear. So I do change the cross-section. Secondly, if my hand is like this, I can feel the tension in my entire arm. When I'm like this, my arm is free. So I don't have tension. So basically, I'm more relaxed. That might make me swim faster. I don't know that, okay? So, most of you, if you look closely, will know that most players today play with curved sticks. Okay? These are not straight. This is hooking to that way, and this is hooking this way. Okay? Basically, they're curved sticks. Why are hockey sticks curved? Anybody know? Yeah. Yes. It makes it much more efficient to catch the puck in this direction. But what it does for this direction, it makes much more difficult, or somewhat difficult, the other direction. Okay? So the reason that hockey sticks are curved is because the world is nonlinear. Now that I know is only for the grown-ups. Here's an example of a nonlinearity in the world. What it means is I'm more efficient if I have a curved stick in terms of scoring by how much I gain with the forehand shot than I lose with the backhand shot. Why, on the other hand, are hockey skates flat on the bottom? They're not curved. That is to say, if you've got a good sharpener, I only have to take mine back about 3 times, that coin sits absolutely square. If you've ever skated on a pair of hockey skates where that's not the case, you'll know about it. Do you know why they're square? Yeah. Well, yes. Some people even are able to fall over when they're square, as a matter of fact. But that's right. The answer really is that you tend to go to the right in the game of hockey as much as to the left. If I only skated around one way, I might think about it, but I don't think speed skates do that. I think at the Indianapolis Speedway, once they did change it so that the cars were shimmed a little bit when they used to have a flat speedway. Okay, so I have quite a few other quick ones I want to show you yet. I want to talk just not about that baseballs curve. We'll show you that they curve. I'm going to throw a ping pong ball out of this piece of thing, and it's going to curve. I was blinded. Could you see it curving at all? Let's try some other ping pong balls. Notice it went that way and then went up. Try it one more time, since we have all these great ping pong balls. You remember when Moshe Bini said, you can't put in what God hasn't put in there? That's why I'm a scientist. That's a hard one to do. That ball went this way and actually rose, okay, because it was spinning. Now, what I want to talk about is not that how they spin. That's too complicated. But how do you throw a curveball? I actually have some baseballs. How do you throw a curveball? Do you want the ball to curve this way, curve this way, curve this way? How do you throw it? Okay, what you need to think about, yeah, go ahead. The bat is this way, okay? If I make the ball curve in the direction of the bat, all I do is get a blimp shot, but I still, if the point of view is to miss the bat, then I might choose to make the curveball curve perpendicular to the direction of the bat. So if you're a little leaguer and you're trying to learn to throw curveballs, work on them curving this way, not sideways. If you're playing cricket, where you've got this thing looks like this, someone ripped off my cricket bat. Anyway, then you want to curve it sideways, because the characteristic distance direction of where you're strong in terms of the batting in cricket is in the up and down direction. In baseball, it's in the horizontal. And as a pitcher, I want to undo it, I go this way, okay? So I just have one quick cartoon that's sort of adult-like. Shows that occasionally you miss something in life and it changes the course of things. This explains something if you think about it. So, finally, I'd like to talk quickly about hang time. Everybody knows that Michael Jordan comes in, dribbles the ball, and flies through the air. He does something and he seems to hang, right? Does he reach over and turn off gravity? I don't think so, right? What does he do? Basically, he jumps high, but, well, we just show this one. This is John Wooden, who was a basketball coach some years back, almost as famous in that day as Seal Berry is today, perhaps. And he said that he would have been disappointed if mere physical strength would ever prove superior against finesse, dexterity, and maneuverability, in other words, grace. And he was really a great basketball coach. Here's an example of physics applied not to basketball, but to dance. This is a dance move, the grand jeté, in which the dancer's head appears to float horizontally because, just like in the Fosbury flop, the hands and the feet are doing those things necessary so that though her mass is going on a curve, like things curve when you throw them, basically her head is going horizontal. I don't know if Michael Jordan does that, but I'm going to guess that he may well be doing it because he has so much grace anyway in what he does. This is a cartoon, you know, Lucy, why is the sky blue? Because it isn't green. And he says, oh, I thought there'd be a more complicated reason. Basically, none of the things that I've showed you today and some of the things I was going to show you but haven't been able, because time goes faster than I thought, require a complicated reason. That science is fairly simple. Now I come to the most difficult part of the whole lecture. This is one where some of my adult colleagues said, it'll never work, Jim. I am going to require of the children in this audience to do something that is really difficult, and I don't know whether we can pull it off. How many of you go to concerts? What happens at the end of a concert? Clap, right? My problem is, in this country, when the concert is over, everybody claps right away. There should be a pause. There should be some silence following a concert where the beauty of the music or whatever you think about it, there should be a thought process. When you leave a lecture, you shouldn't just you should actually walk out carrying with you some thoughts. Now I have some thoughts, and I even have some music that we're going to listen to. Well, this is really tricky, and I'm going to see whether the kids can do it. I want you to think about physics as a way of thinking, efficiency of motion, universality, how the chalk drops everywhere here and on the moon, and how it applies in many places, while we listen to sort of a benedictual piece of music, which I consider gorgeous. It's Russian music, so you don't have to worry what it's about. and we just listen silently. And I want you, as kids, to think about the swimming of the hands, how you can apply what you've sort of done. You could do this at home. You could do it in the bathtub. You could do these sorts of experiments that we've tried. And just think about it, and don't make any noise. Just listen. So let's push play. This wizard thanks you for coming and thinking with me. Thank you.